And as you can see, we can do some measurement on the RSSI on the radio itself, and this has been very useful to actually have this measure. Our ground station is a standard UHF radio amateur station. We have the ICOM 910H, Yaesu DS5500, and then we have the a home-built CIV level converter and the Howard LVB tracker, if any of you guys know that. And then we have because we have this this modem here, this is a finished chip. In the other end, in the ground station, we also have a modem that features the same chip from the same manufacturer, of course, which runs GMSK at different speeds, and then we run a X25 on top of that. And this has been a bit of a difficulty because not many radio amateurs actually has a TNC that supports GMSK. So it's another modulation scheme that not many people has, and therefore our satellite is not directly supported for receiving data by radio amateurs. But radio amateurs can download a software to demodulate the if they got an audio recording, they can download software and demodulate that, and from the demodulated binary data, pass it through another application that gives them all the telemetry. So we work together with the radio amateur community to well, we have created a solution that requires special equipment to receive, and then we are working together with the radio amateur community with providing facilities to demodulate and decode our telemetry. Here's a picture of our testing application where we do some uplink and downlink. It's just not that interesting. Of course, when we've finished building this, we have a lot of testing, and to the left we see the EPS, the power supply in the vacuum chamber, and due to our unlucky experience with our antennas in Amsat 1, we actually went on a parabolic flight and tried to unfold our antennas in 0G. So we know that also worked. And here's just oh shit. Okay, it's early in the morning. Here's just a slide with some pictures from the integration phase. To the top left, you see the coating that goes on our PCBs. I think it's just an epoxy coating. I'm really not into all the details about the integration, but we do this to ensure that nothing goes loose during the launch, and also to make it more robust. And to the right, you see our in the beginning, quite unique frame, but now people has more adapted to this. It's built out of one solid 11 by 11 by 11 aluminum block that has been drilled out from all sides. So it's very strong because it's a solid block instead of connecting the frame out of 2 or 3 pieces. And that means that we can save a lot of weight on the spacecraft, and therefore we can also have larger batteries. So, and actually the final spacecraft only is 700 grams, which is pretty much below the specification. And down here you see the stack, and the way we did it was just with a on a stack connector that we plug them on top of each other, and we have the power lines and the CAN bus in there. So now to the interesting part, obtaining the space link. Now we kick this satellite out in the space. We had a very successful launch. It was delayed 1 minute, and that's a lot when you look at the TLE. And also, we have this unavoidable problem that we need accurate TLEs in the beginning. And especially for our case, we needed very accurate TLEs. in order to decode the data because we had this antenna problem. I'll come back to that. What we saw was very bad signals. And what to do with very bad signals? We got varying signal strengths doing a 1 second beacon. And we can see this on the, we transmitted to it at one point and got it to transmit 30 seconds of housekeeping data. And we can see how the signal strength actually varies during the reception of the data. So in between, we would actually not be able to decode all the places where we have a peak up there. And that's a bit difficult to work with when you don't have good antennas. And we learned that from the first spacecraft that antennas need to be good, and then we fucked up again with ASat2. It's mainly due to that our so the conclusion was that our antennas is not correctly unfolded due to the spacecraft being delayed for 1 year on the ground. The launch was delayed 1 year. So the antennas lost some tension, so they didn't kind of spring up correctly. We had a big problem. And to add to this problem, we also had a high tumbling rate, which means that the spacecraft rotates a lot. And if the antennas has a dead spot and it rotates a lot, there will be a lot of times where we cannot hear it. So we took some countermeasure. We upgraded our downlink with 4 new LNAs inserted before our antenna combiners. This gave us approximately 2 dB more. And then we switched cables and got new connectors, and that gave us approximately 1 dB or so. But a 3 dB gain in SNR is pretty good for a ground station on the downlink section that is pretty optimized already. So we were happy with this 3 dB gain, and we were actually able to take some beacons down. In a typical pass with 20 or 30 beacons, we can now decode approximately 10 or 15 of them. But then we needed to try to talk with this spacecraft. We asked on a Danish engineering forum where also radio amateurs listen. This guy to the left, I don't remember his call sign, but he came with his home-built 400 watts power amplifier unit that he built from old Russian World War parts. Really crazy guy. But this actually gave us pretty much. We were, before we had an RSSI of minus 97 dB, and we need 90. So we need 10 dBs more somewhere. And this PA unit actually gave us these 10 dBs and more to that as well. So now we've bought a kilowatt preamplifier to ensure that we can talk to the spacecraft continuously. So we actually succeeded talking with our spacecraft now. We commanded it to downlink housekeeping. We commanded it to downlink scientific data from the payload that we have on board. But there's still some recommendations that we would like to make. And these recommendations are mostly for spacecraft designers. But they have some relation to radio amateurs as well. Actually, we think that it's very important to keep a continuous or a frequent beacon. CW or anything is good. It's just for locating the spacecraft. We used the good part of a whole day just listening to passes and trying to predict where our spacecraft was. And we have a beacon every 30 seconds. That's a long time to sit and wait when you tune into a frequency and sit there and wait, is it on this frequency? So therefore, we recommend that that the space link is kept at the lowest capacity in the beginning, possibly just a CW beacon, and then by uplinking to it, activating the higher modes, so the 1200 baud FM or so different modes. And then what I'm looking into in Amsat 3 is what is the modulation of the future here? Because doing FSK, which is frequency modulation, we modulate a binary signal down to audio, and then we transfer it again through an FM channel of possibly, well, 20 to 200 kilohertz in the frequency spectrum. And you just put it into your ICOM and it converts it. It's a waste of bandwidth, really, to do double frequency modulation. So there are some new interesting software radios that actually provide some sideband modes or the possibility of just up-converting your FSK or down-converting it again, so that you can get better speeds and at lower bandwidths. So with the same bandwidth, you can put more stuff into it. You can add redundancy to make your signals or to make your beacons even more robust. So that is one of the really good questions that we got to sort out for Amsat 3, because I think we already got sorted that we are not going to stick with FSK much longer. Already for Amsat 2 we have upgraded to GMSK, which is more polite, so to speak, in the frequency spectrum. But we have the problem that many TNCs are still hard-coded for FSK. So it's always a trade-off between the radio amateur community and how much innovation and new stuff you would like to put into your spacecraft. And then another thing about the protocol. AX25, we don't have any forward error correction. And I think it's a bit stupid because out of our 30 beacons that we get in a pass, we could actually receive much more information if we just got a bit of forward error correction. We look at the signals, it's almost a perfect beacon, but just 1 or 2 bits, the checksum is wrong, the whole frame is skipped. So therefore, we're going to look into what we can do to improve the X25 protocol. And I know there's already some different ideas out there. So, and then we would like to use in the beginning. You're really only interested in one bit of information, and that is your spacecraft is working and transmitting. So that's just receiving the beacon. After that, you're only interested in knowing the voltage of your spacecraft. So why not transmit a whole frame only containing voltage for a period of time where you have a lot of redundancy? So instead of keeping a large beacon with a lot of information, use varying levels of redundancy and put more data into it as your confidence and as your quality in the space link increases. Some slides about Amsat 3, not done by me, so I can just tell you a bit about the mission. The mission is quite interesting actually, Amsat 3 will be a radio platform. Amsat 3 has the goal of going out in a polar orbit around Greenland and picking up AIS signals from ships. And these signals are on VHF, transmitted with GMSK 9600 in a TDMA scheme. And this TDMA scheme is what is giving people all the headaches with regards to AIS. I should say AIS is the navigation sort of information exchange system for ships. Any larger ships above 200 tons or so have to have an AIS transmitter stating their GPS coordinates, their speed vector, their cargo, where they're going, and everything. And this, in the Danish waters, it has been a very successful implementation of the AIS system, because previously all ships was going around the seas in a big mess, but now that ships can see other ships that are not visible on the radar exactly, they have very nice systems where they always pass right of each other, and that's a bit different to over here where they pass left on each other. But it's it has really increased the safety in the Danish seas to have this system. But Denmark also has Greenland, and well, that's a big thing in Denmark, that every time we do one thing in Denmark, Greenland wants to do it as well. But what to do about Greenland, because they have so large coast areas, and AIS signals can only go to the horizon, and with the curvature of the Earth, it's around 50 kilometers in a radius from the ship. But we cannot place receivers each 50 kilometers along the coast of Greenland, because it would be so expensive. And also there's no power, there's no infrastructure in Greenland. So the Danish Royal Administration of Navigation really would like to have a spacecraft that can pick up these signals, so they can get an overview of the entire sea around Greenland. And that is our mission, to go out there and pick up these signals. The only problem is that these signals are TDMA scheduled, and they have a collision avoidance, that they listen to whatever is in a minute, and then they record the time information, and they register in a time slot. But what happens now is that two ships are in two different parts of Greenland that cannot hear each other. And these two ships transmit at the same time, because their collision avoidance don't know anything about the other ship. And when we are up here in the spacecraft, we have now colliding messages. So how do we extract two different messages from two ships on the same frequency at the same time? And that's a big topic, and we have a lot of research in that. And I know that the Canadian Space Agency has also some initiatives there. So ASAT 3 doesn't have a solution for this problem. But what we will make is a radio platform that is able to recording at a high sample rate, just a few seconds of signal, because then we can downlink this and analyze very closely in the laboratory. But we will also add the feature of relaying VHF to UHF, sort of like AO27, where you can hear people talking. Then we will be able to downlink, if we have a ground station in Greenland, we will be able to downlink the data from up there. So that's the mission. I won't really get into all the research stuff. I think I have bored you enough already. But thank you very much. So.
Thank you very much. So do we have any questions? Yes.
When is the launch planned for our Amsat 3?
Could you repeat the question?
Yes. The question was when the launch of Amsat 3 was planned or scheduled. We don't have a flight yet. So we don't have an exact date. And even if we did have a flight, we have experienced that these launches get delayed. But as a rough time schedule, around 2010, we will be able to come up with something before that if we have a flight opportunity earlier. But if we look at the academic perspective, we have to get students involved in it as well, and they need to start up on the project, have a design phase and then an integration phase, and all this takes time. So, so we would like to give it the time that the students need to do it, because it's not the PhDs or the employees at Aalborg University that does this. It's only the students that do all the work. So, good question. Thank you.
Any other questions?
Coming back to your AIS question, the satellite will see a good deal more than Greenland. So there'll be many other vessels, particularly in the North Atlantic, going backwards and forwards. So what would you do? Would you in some way try to keep a log, and so you only selectively listen to particular vessels? Because I mean, somebody doing the North Atlantic run isn't really interested in what the Greenland coast, or vice versa.
Yeah.
So do you plan to sort of have kind of a logging mechanism so you only relay things that you've decided you want to relay?
We cannot decide what to relay.
With the AIS system, you see the ship's ID, so
Yeah.
you could say, I don't want this ship and I want this one.
If you decode the data on the satellite, you can choose, of course, what to downlink from the satellite.
Yeah.
But the problem is that AIS could be difficult to decode on the satellite. Of course, there are off-the-shelf products for decoding these GMSK 9600, and then you have other chips that actually does the telemetry unpacking for you, that can do everything actually.
Yes.
And there's a lot of software for it as well. So
I think there's quite a lot of receive-only systems.
yes.
Not least of all, the military
Yes.
don't tell you
So
who they are.
of course we take some of these receivers and stick on the satellite as well, and see, do they get any good information?
They're very small.
Yeah, we're very interested in the rate of detection. So if we know that we pass a ship, what is the not the
What, you mean the
well, the
collision?
probability, that was the word. The probability that this ship will actually be detected. It needs to be close to 95 or so in order for this to be really good. Otherwise, we would have to take another pass around the Earth, and the ship wouldn't be there anymore. So we would like to get a high probability of detection, and that's why we do this the way we do.
Okay, thank you.
Okay, I think we've time for just one more question.
Sorry for hitting this nail once again, but I mean, you talked about improving AX25 with forward error correction.
Yes.
Have you ever looked into the possibility of just copying the AO40 telemetry format? Speaking about 400 PSK.
400 and just 400.
Just 400
Just
bits? Because 400 bits with
yes.
99% efficiency is better than 1,200 bits.
Yeah. It is a kind of redundancy.
Can you repeat the question? So?
Okay, the question was if we have considered going lower in the bit rate.
Right.
Yeah, and actually that's a yes. We would like to have the possibility of going lower on the bit rate, but modulation is usually done in a chip. Otherwise, you would need some kind of software processing of the audio in a microcontroller, and that takes a lot of power. So
Well, that's actually not true for PSK. You just take the mixer
Yeah,
and modulate
yeah.
one of the inputs with your bits.
well, I'm not a radio guy, but I think yes.
It's even more easy. It's much more easier than NSK.
Yes. Okay. But we would actually very much like this, because we believe that the possibility of having multiple modulations on there will actually increase the possibility that we have successful communication with it.
Well, I mean, in terms of the specific reason why I keep on banging on this 400-bit PSK is, you might not be aware of this, but the amateur radio satellite community has had, I like to say, tremendous success with implementing this on Amsat Uk 40. And with a telemetry frame of something like 10 seconds for the complete frame, you could cover, or you could really unplug the antenna cable for 3 seconds.
Yeah, and it will still work.
Yeah.
See, that's very great for tumbling.
Exactly.
Because you saw that for actually 1 second we don't have a signal, and and that's very good. Yeah, so definitely we want to go into that kind of stuff with AOSAT3 to make sure that we get the base space link up and running no matter what. So even if the spacecraft is pointing the other way with the antennas. So, but thank you very much.
Thank you very much. Well, again, let us thank Johan for a very interesting talk.